In the sky? You mean flying? So you want to learn to fly?
Welcome to the world of paragliding. The aim of this film is to introduce you to this amazing sport and to explain the basic skills and theoretical knowledge that are essential for a long, safe and rewarding flying career. Man has always dreamed of free flying, the ability to fly like a bird and view nature and landscapes from a different perspective without the need of an engine or cumbersome machine. With paragliding, this is possible. All that is required is the correct equipment, training and knowledge. A paraglider is a foot-launched, ram air aerofoil canopy designed to be flown and landed with no other energy requirements other than the wind, gravity and the pilot's muscle power. Paragliding offers different types of flying and is a very personal thing, whether it be gently soaring flights in smooth air or epic cross-country adventures in strong thermals, or even radical aerobatics. The choice is yours. In any case, keep in mind that safety is the most important issue for a long flying career. Regardless of the direction you take, right now you're at a stage that all of them have in common: your initiation. Paragliding is organised within each country by a national federation. Their role is to oversee the sport as a whole, regulating the quality of training, organising insurance, and securing the rights for pilots to continue flying with all the current restraints on airspace. The quality of the training you receive is extremely important, as it establishes a strong foundation of learning and skills that will carry you throughout your flying career. Paragliding is a potentially dangerous activity. It's important that you're aware of this fact before going any further. You'll have to carefully evaluate the quality and reputation of the training you intend to receive. Many schools offer quality training courses encompassing both theoretical and practical aspects of flying. This DVD does not replace proper training in a recognised school. It is intended to be used as an aid to your learning experience, so that you can review any stage of your training in your own time. We will use animations to help visualize the theoretical course material dealing with the aerodynamics of flight, meteorology, and regulations. Experienced instructors will show you how to perfectly inflate a canopy, using both the forward and reverse techniques. This will give you an idea of the skills you should be aiming to learn. So you've decided to learn how to paraglide. It's probably one of the most exciting things you will have done in a long time. But remember, safety and fun are the main priorities. You must stay within the limits of your experience and be progressive, and don't skip over any of your training stages. Learning how to paraglide never ceases. There is always something to learn and improve on. This is one of the many factors that makes it so intriguing and addictive. We hope you enjoy this film. Good luck with your training and future flights.
The wingspan averages about 10 to 12 meters and the chord measures 2 to 3 meters. The chord is the greatest distance between the two edges of the wing. Its surface area ranges from 20 to 30 square meters. The section of the wing in red is called the leading edge. It has openings which air flows into when inflating and then during the flight, hardening the wing into its characteristic shape. The rear section of the wing in the foreground of the image is called the trailing edge. Here is where the upper and lower surfaces of the wing reconnect to form an airfoil. The extremities of the wing are called stabilizers. The surface of the wing on top is called the upper surface. The surface of the wing on the bottom is called the lower surface. The hollow space between the upper and lower surfaces is separated into several cells by ribs. The openings we see here are used to inflate the wing. The circulation of air between cells is made possible by holes in the ribs. Near the leading edge, the fabric used for the rib is much more rigid. Nylon or polyester threads are meticulously stitched to make the fabric flexible and light, while at the same time extremely resistant.
The wing is connected to the harness by carabiners. These carabiners are considerably oversized and can withstand weights exceeding 2,000 kilograms.
There are several different locking systems. Auto locking, as seen here, twist locking, or screw gate locking. Moving up towards the wing, we first come across the network of risers. Each riser, usually 3 or 4 of them depending on the model, is attached to the suspension lines, which in turn are attached to the wing. Attached to the rear riser is the braking system. The brake line is directly linked to the wing's trailing edge and slides along a pulley. At the end of each riser, a triangular quick link connects a group of suspension lines from a section of the wing.
Moving from one riser towards its group of suspension lines, you'll notice that the lines branch out twice into mids and uppers. The A risers, or front risers, are attached to the leading edge. The B and C risers are attached to the middle, and the D risers, also known as rear risers, are connected near the wing's trailing edge.
The distribution of the wing's suspension points places uniform stress upon the entire wing, thus giving it the correct airfoil shape and also helping to evenly distribute the pilot's weight throughout the wing.
The harness is where the pilot sits.
The first noticeable element of the harness is the compartment sticking out on the side. Known as the container, this is where the reserve parachute is located. The reserve parachute's deployment handle, here in red, is located at the top of this pocket.
The parachute straps leading out of the container are anchored to the harness near the shoulders using carabiners.
On the back of the harness is the storage compartment. This compartment is usually used to store your paragliding sack during the flight. Also located on the back and bottom of the harness is the bag protection. There are 2 main types: airbag protection or, as shown here, foam bag protection. The pilot sits on this seat board inserted in the harness, which makes it comfortable and allows the pilot to transfer his weight to control the wing. Let's look at how the pilot is attached to the harness. The harness is attached to the pilot in 3 important places, all 3 of which must be verified before every flight during the pre-flight inspection. First, the leg straps, which are easily fastened thanks to a quick lock buckle. Being able to slide your hand through is a good indication of how tight it should be. These straps need to be appropriately fastened so that the pilot is comfortable during his takeoff run. A little higher is the chest strap, which often has a threefold locking mechanism. In the center is the safety strap, which is there to remind you by its color and position to buckle up. Some older type harnesses do not have this. Instead, there's a single buckle. Adjusting the chest strap is simple, and by loosening it, the pilot's weight can be more easily shifted during the flight, making more maneuvers possible. However, when flying through turbulent air, the pilot may find having a chest strap too loose or too tight. It also affects the safety above of the glider. The shoulder straps need to be adjusted so that the bottom of the harness is level with the middle of the pilot's thighs. If the straps are too loose, the pilot may encounter difficulties during the takeoff run, as well as during the transition into a seated position. By tightening these straps, the pilot makes sure that the harness is adjusted to his size. A comfortably fitting harness is an added safety precaution. It makes flying easier and prevents the pilot from being uncomfortable during his flight. The objective here is not to teach you how to fold your reserve parachute nor how to use it, which may be done at some point during ground school. Rather, the goal is to raise your awareness about the issue and to help you visualize a parachute that is rarely seen during the training. It's a piece of fabric in the shape of a hemisphere with a hole in the center. It's important to understand that the reserve parachute is your last resort in case of an emergency. For that reason, it's crucial that it functions properly. That's why you should ask experienced instructors to help you fold and pack your parachute. Learning how to do this yourself during ground school is also recommended. The folded parachute is placed in the deployment bag. Once packed in the pod, it is then placed in the compartment on side of the harness called the container. As far as maintenance is concerned, your parachute should be aired out regularly. Unfolding, inflating and refolding it twice a year is recommended. You've probably been wondering what makes these pieces of fabric fly, why all of the gliders typically have the same shape, or even how this flexible structure manages to stay aloft above the pilot's head. Our focus on flight mechanics in this chapter will attempt to provide answers to all of these questions. At the very least, it will give you the basic understanding you'll need to pilot this peculiar aircraft. Let's start by looking at the basic shape of our paragliders. In this animation, we'll demonstrate the importance of the wing's profile. The goal is to optimize its penetration through the air and reduce drag as much as possible. We're going to see what happens to the air as it flows over these three profiles. Looking at the first profile, a simple plate, the molecules of air contained in the airstream are completely blocked in the middle. The air that flows beyond the plate is turbulent, which significantly increases drag. The airflow over this profile is similar to what happens when rowing a boat. The oar needs enough force to displace water, and as it displaces the water, small eddies form behind it. The second profile penetrates the air a lot better, as we can see here. The result is a much smoother airflow. The molecules of air flow smoothly over the front of the profile. However, too much drag is still created by this profile. The third profile has been improved so that the airflow is smooth from start to finish. Our profile will travel through the air with little resistance thanks to its cambered shape. It will also reduce drag by replacing the air in its wake. This is an ideal aerodynamic profile. If you were to cut the Paraglide in half, you'll find this cambered shape along the entire wingspan from the leading to the trailing edge. This is how manufacturers optimize the wing's penetration and movement through the air. But this doesn't explain what makes a paraglider fly. Let's move on to a phenomenon that you've probably already heard of: lift. Let's take another simplified cross-section of our wing and observe what happens as air flows over its profile. In flight, the angle created by the paraglider's wing and the relative wind is called the angle of attack. As the molecules of air come into contact with the wing, they are separated into two streams by the leading edge. The first stream flows along the upper surface of the wing, the other along its lower surface. Even though the upper surface is longer than the lower surface, experiments have shown that both air streams reach the trailing edge at the same time. There's only one way for the molecules taking the longer route along the upper surface to arrive at the same time: they have to accelerate. Thanks to a principle formulated by Swiss mathematician and physician Bernoulli in 1738, we know that as the speed of a fluid increases, its pressure decreases. In other words, the faster moving air over the upper surface of the profile creates a low pressure zone on top of the wing, which is the source of lift. On the other side of the wing, air molecules push against the lower surface, creating a high pressure zone. This is also a source of lift. About 3/4 of the lift results from the low pressure above the wing and 1/4 from the high pressure under it. Most of the lift occurs near the profile's leading edge. This simplified explanation of what causes lift should help you understand why our wings fly. Lift is thus created by the flow of air over the profile. But how is this phenomenon sustained when there isn't any wind? What is the paraglider's motor? In order to answer these questions, we'll turn to the science of mechanics. This science deals with the action of forces on bodies. The forces we're interested in are those that act upon the pilot and paraglider. Let's start with a simplified model of the low and high pressure zones: lift. This force acts upon a point known as the center of pressure. This point is merely an average of the lift forces acting upon the paraglider. When traveling through the air, the paraglider encounters resistance and creates turbulence in its wake. The force that opposes its forward movement is known as drag. Since these are the two main forces that act upon the profile, we can add them. Their sum gives us the resultant. How do we obtain the relative airflow necessary to create lift when there isn't any wind? By simply transferring his weight to the wing, the pilot pulls it towards the ground, forcing it to move forward through the air. This movement we call airspeed, and this creates the relative airflow required to produce lift. Altitude, therefore, is the paraglider's energy reserve, and by using our weight to draw on this reserve, we're able to fly. As mentioned before, the angle of attack is the angle at which the relative wind meets the profile. This angle should not be confused with the angle to the horizon, known as attitude, as it's possible to have a relatively high angle of attack with the wing at any attitude. In normal flight, the paraglider remains at a constant angle of attack and at a constant airspeed. The pilot can influence the angle of attack and thus the speed by using the brakes or speed system. The angle of attack and airspeed are very much related. If you change the angle of attack, the airspeed too will change until a new equilibrium is achieved. The angle of attack can be increased by applying the brakes evenly. This causes a corresponding decrease in airspeed. The greater the angle of attack, the more lift is produced. However, more drag is also produced. If too much brake is applied, then the smooth airflow over the profile cannot be maintained, and the airflow breaks away from the top surface. This is known as a stall. Being aware of the stall is very important when learning to fly, since inadvertent stalls are very dangerous and should be avoided. Always keep your hands high and make sure you feel good airspeed on your face whilst flying to avoid the stall. Only when making the landing flare should you use deep brake inputs. The angle of attack can be decreased using the accelerator system. As the angle decreases, drag is reduced and the speed increases. The glider continues to accelerate until a new equilibrium is found. The wing then stabilizes at this new speed and sink rate. At low angles of attack, paragliders are more prone to collapse. This is why you should not use the speed system when close to the ground or flying in turbulent air. Let's turn to the concepts of lift to drag and glide ratios. The lift to drag ratio is the angle at which the paraglider glides. These concepts will help you understand why this student barely manages to lift off from this slope. They are simply ratios that measure the glide capability of your wing. These ratios are obtained by dividing the horizontal distance covered by the vertical distance lost. In this example, 750 meters divided by 100 meters gives us a ratio of 7.5. As you may have guessed, the greater the horizontal distance is, the greater this ratio will be, and the longer you'll glide. This is called your lift to drag ratio. It's a technical specification of your wing. The lift to drag ratio doesn't change unless the wing is damaged. We'll see later on in the flight chapter that the wind or micrometeorology can influence the trajectory. The distance covered will vary, and in this case, we'd refer to its glide ratio. Let's go back to the example with our student. He can't lift off because his lift to drag ratio is too close to the angle of this slope. For launches, we'll need a hill whose slope is steeper than the lift to drag ratio of our wings. Modern paragliders have a lift to drag ratio between 6 and 10 to 1. For reference, you can compare this with a lift to drag ratio of 15 to 1 for hang gliders and almost 60 to 1 for sailplanes. Paragliders have a large speed range, and knowing when to use these different speeds is very important. You have control of the speed with the brakes and the speed bar. This is known as speed to fly. Knowing to fly at the right speed, depending on conditions or the site, is the basis of safe and efficient piloting. Understanding different flying speeds will make you a better pilot. The correct speed and just the right timing makes it possible for this student to make a smooth landing. As a general rule, when in lift slow down and when in sink or headwind speed up. This increases your efficiency and prolongs your glide performance. Flying at trim speed, your glider will achieve its best glide angle in calm air. The pilot's arms are high with no pressure on the brake handles. At this speed, the profile isn't warped in any way and therefore creates the least amount of drag. Flying like this will allow you to cover the maximum distance. Most modern paragliders have a trim speed of around 36 or 37 kilometers per hour. When learning, the main reason for flying at such a speed is to accelerate before landing and build up energy that will eventually be converted into a flare. This makes a soft landing possible. Flying at trim speed also reduces the likelihood of problems caused by the wind gradient, such as inadvertent stalls or sudden altitude loss near the ground. Apply the brakes approximately 30 to 40 centimeters to reach the minimum sink rate. The pilot's arms are about level with his shoulders or just below, and there is a positive pressure through the brake handles. Applying pressure to the brake handles will also improve your sensitivity to the wing's movements and increases the internal pressure and angle of attack of the wing, which reduces the likelihood of collapses. Flying at min-sync increases the angle of attack and significantly increases drag, which reduces the ability to glide and consequently reduces the distance that can be covered. However, flying like this gives you the slowest vertical speed. In other words, you sink at the slowest rate. You can take advantage of this when flying in lifting air. Note also that other than the landing flare, it is never necessary to fly slower than the minimum sink rate. Inflating is probably one of, if not the most important technique to learn when starting out. That's why the first day spent practicing it at glide school usually stands out in a paraglider's memory. It's the first contact you'll have with the equipment and is usually accompanied by your first uncertainties. It's also the occasion for instructors to give invaluable advice. At this stage, you'll learn how to correctly handle your equipment, observe your environment for ideal conditions, and concentrate. Above all, you'll learn how to properly inflate the canopy and make a good run, the two prerequisites for a safe launch. Pay attention to what your instructor says. He'll explain all of the basic techniques you'll be expected to develop throughout your training. Launching is the most hazardous moment of paragliding. Most accidents occur during the launch. Make sure you know what you're doing. Practice regularly your ground handling techniques. With enough practice, you'll be making beautiful and safe launches in no time. It's the first step to a successful flight. Preparing the equipment and going through the pre-flight safety inspection must become second nature. Being strict and using a simple but effective methodology will prevent errors and give you all the more chances to make safe and successful launches. Start by laying your wing out on the slope.
A wing is always inflated facing the wind. Facing the wind, you'll find it much easier to obtain the relative wind needed to create lift. It will also make shorter launch distances possible, which can be useful for certain sites. When launching, several different scenarios are possible. A headwind, the ideal situation. Using this configuration, orient your wing so that it's facing downhill and into the wind. A crosswind. The wind is no longer blowing along the launch axis. Launching is still possible, but it will require more skill. Orient your wing so that it's facing the wind and inflate it. Once the wing is inflated and stabilized over your head, adapt your launch run so that it brings you back into the launch axis. Launching with a tailwind is impossible. In a scenario where there isn't any wind, orient your wing so that it's lined up with the steepest slope. Don't hesitate to reposition your wing along its entire wingspan so that when you're ready to inflate it, its layout is ideal. Some pilots recommend laying it out in a slight V shape or in the shape of a horseshoe so that both halves of the wing inflate evenly. Considering the new orientation, reposition the harness in the center of the wing. Notice how Christopher has positioned himself. The lines are almost tensioned, which will make it easier for him to untangle them. Take hold of the risers at the carabiner and make sure they are untwisted. Hold the A-risers in front of you. Isolate the A-lines, then work your way towards the wing and verify that they are free of twists, tangles, knots and debris all the way to the leading edge. We can clearly see here that they are located underneath the other lines. You'll have to untwist the harness. Start out by correctly repositioning the lines, then continue to untwist them up to their base. This method makes it easy to figure out which way to spin the harness in order to eliminate the twist. New verification. Make sure the lines are free all the way to the leading edge. The harness is now on the ground without any twists. It's time to untangle the lines. As we saw earlier, Christopher isolates the A-lines and puts some tension on them as he works his way towards the wing. Often, you can verify that the lines are not tangled or knotted by simply putting tension on the lines. Do the same thing for each set of lines. Untangling the lines can be done rather quickly and easily if you put the right amount of tension on them. Christopher is now ready to put on his equipment and the harness. The pre-flight inspection begins. Remember to check your reserve parachute rubber bands as well as its handles to avoid pulling it by accident during the launch or the flight. You can put on and attach the harness. Inspect and fasten the leg straps at the same time. You should be able to slide your hand between your leg and the strap. Fasten the abdominal strap next, followed by the chest strap.
The pre-flight continues. Christopher inspects his carabiners, then each quick link, and finally the connection of his brake handle. Now you're ready to grab your glider's controls. Let the risers hang down untwisted alongside your legs, unhook the brake handle, then go under the network of risers so you come up grasping the A risers. Then double check that the A risers are completely free up to the leading edge. In addition, make sure the brake line isn't blocked. Do the same thing for the other half of the wing. You're ready to launch. There are two different ways to inflate the wing, either facing the wing called reverse launch or with your back to it called forward launch. It's a good idea to master both techniques because each one has its advantages in different conditions. In general, use forward launch in light winds and reverse launch in wind over 10 km per hour. That way you'll be able to choose the most suitable technique according to the weather and the terrain. Let's first look at a forward launch with your back to the canopy. Pilots usually use it when there is little or no wind, since it provides continuity throughout the thrust, inflation, and launch run, and thus prevents the wing from collapsing. Jerome Cano, a test pilot with Ozone Paragliders, is going to take us through the steps and techniques of a flawless inflation. The wing is correctly laid out facing the wind. Then the pilot positions himself in its center. He's ready to give the thrust. You need to provide enough thrust so that the wing rises evenly until it's just over your head. Be careful, the thrust you'll give depends on the wind speed. If the wind is strong, especially when performing a reverse inflation, give very little thrust, otherwise you'll be yanked off the ground. The wing climbs until it is directly over your head. To prevent it from overrunning you, use the brakes to control it. Without this control, the wing will overrun you, lose its lift and collapse. At this point, you can visually inspect your wing to make sure it has the right shape and that there aren't any knots in the lines. Now's the time to decide whether to continue or abort the launch. You're ready to start your launch run. Notice Jerome's position. He is leaning forward with his shoulders sticking out beyond the risers. To abort your launch, pull the brakes all the way under your backside and continue to advance until the wing falls behind you. As you can see, a forward inflation is also possible in strong winds. However, a reverse inflation is more suitable for strong winds. It enhances the pilot's ability to control his wing. If he needs to reduce his force, he can walk uphill towards the wing without the risk of falling. Pilots tend to prefer this method since it lets them see the wing during the entire inflation process. Let's take a look at the two main techniques for grasping the risers. Start out by spinning to face the wing in the direction that seems most natural to you. The risers should be crossed in front of you. The first technique, known as cross-brake reverse launch, allows the pilot to inflate the canopy and then launch without letting go of the brake handles. Jerome takes the left brake handle in his left hand, then the right brake handle in his right hand. Then he grasps the risers in front of each hand. Let's go over again from the beginning how he grasps the handles and inflates the canopy. Jerome can launch without ever letting go of the handles. Notice the skill involved in each step: inflation, timing, visual inspection, spinning, filling the wing. The second technique used to hold the controls is referred to as the uncrossed hands technique. Let's go back to the situation where we're facing the wing with the risers crossed in front of you. This time, Jerome takes the left brake handle in his right hand and the right brake handle in his left hand. In other words, the handle located in front of each hand. Then he grasps the risers in front of each hand. Some pilots find it easier to control the wing using this technique. Its one major inconvenience is that the pilot has to momentarily let go of the controls at the important and potentially most dangerous part of the launch, when the pilot makes the turn. The paraglider is a pendulum-like system. In the air, without any stress acting upon it, it will naturally tend towards equilibrium. What this means is that in the air, if the wing recedes behind or advances past the pilot will automatically be brought back under it. Likewise, when the wing swings to the left or to the right, the pilot and his equipment are brought back in line by the pendulum. On the ground, everything is different. If the wing goes one way, the pilot needs to move to get back underneath it. The pilot must act as the pendulum whilst on the ground. During a launch, if your wing rises unevenly, don't panic. It's easy to recover from the situation and make a normal launch. The first thing to do is follow your wing while at the same time trying to correct its course with the opposite brake handle. Once you've managed to get the wing stabilized above your head, you're ready to start your launch run towards the exit corridor. Look at this example with Jerome. His wing is rising unevenly and is abnormally centered in relation to the wind. He'll know from experience to get under the wing while correcting with the brake handles. Having stabilized the wing, he'll be able to spin and start his launch run. As you've just seen, getting the wing to rise evenly depends on how well it is centered in relation to the wind. When launching, use the wind to slightly pre-inflate your wing and check your centering. The two halves of your wing must be at the same height. With experience, turning around will become second nature. However, during our first few inflations, sometimes we're not quite sure which direction to turn. There's an easy way to remember. Look for the riser on top. This is the direction you have to turn. Inflating in strong winds is possible but requires a great deal of skill. A lot of launch accidents occur when strong winds are present. Here's a hint to reduce the force of your wing during the inflation. Only use the central A risers to inflate canopies that are equipped with 4 A risers. This way, only the center of your wing is tensioned while inflating. Its force is reduced. The most important thing is to practice as much as possible inflating on the ground. It'll put you at ease and provide you with all the techniques you'll need during a launch. You now know how to correctly prepare your equipment and make beautiful launches all by yourself. Let's go over some wind-related aspects of conditions that you'll be able to use to modify your flight path. During flight, it is possible that you will come across lift and sink along with headwinds, crosswinds, and tailwinds. All of these will directly influence your trajectory. It is important for your flight plan, and especially for your landing, that you understand all of the ways in which these conditions can affect your trajectory. To make sense of what follows, you need to remember that a paraglider advances and falls at the same speed as the surrounding air. The airspeed and lift-to-drag ratio are technical specifications that do not change unless the canopy is damaged or worn. However, the air that surrounds it can move in all sorts of directions. That's why we also refer to the ground speed and the glide ratio. These values tell us the speed at which the paraglider advances and falls, but this time in relation to the ground. First situation. In a calm and stable air mass, without lift, sink, or wind, the paraglider's trajectory will not be disturbed. It'll approximately fly at the speed specified by the manufacturer. The same applies to the sink rate, which also figures in the technical specifications. In this example, the ground speed and the glide ratio are roughly the same as the airspeed and the lift-to-drag ratio. Second example. The paraglider is flying into a 15 km/h headwind. In this case, the horizontal ground speed is reduced. It can be easily calculated by subtracting the wind speed from the paraglider's airspeed, since they are moving in opposite directions. 37 minus 15 equals 22 km/h. Though its ground speed has decreased, the paraglider still falls at the same speed. Thus, for the same altitude, it runs a shorter distance. Its glide ratio has decreased. A new example. The paraglider in this case will cover much more distance. The glide ratio has increased. Here's another example, this time with a 35 km/h tailwind. The paraglider's speed will be close to, if not more than, 70 km/h. This is why cross-country flying is usually done on days when wind conditions help the pilot reach his destination, and also why pilots always land into the wind. Wind is what causes an air mass to move. Depending on your orientation, these movements can increase or decrease your glide ratio relative to the ground. They also cause drifts that you need to compensate for in order to maintain your heading. Besides the wind, other factors disturb an air mass and cause it to move vertically. Flying through a thermal lift or a downdraft can also influence your trajectory. As a reference, let's start with the trajectory of a paraglider in a stable air mass. In the absence of lift or sink, the sink rate is approximately 1.2 meters per second. In this case, the trajectory corresponds to the canopy's technical specifications, which means that its glide ratio is the same as its lift-to-drag ratio. Here's a new situation. The paraglider comes across a warm pocket of air called a thermal that is rising at 3 meters per second. As he enters into it, he is carried aloft by the rising air. His altitude will increase and he'll be able to use this additional fuel to cover more distance than if he were in a stable air mass. Whilst the glider is in the thermal, it continues to descend at its sink rate of 1.2 meters per second. But, since the air mass it is flying in is rising faster at 3 meters per second, the paraglider will gain altitude in relation to the ground. The climbing speed will be 3 meters per second minus 1.2 meters per second, which equals 1.8 meters per second. You may have already guessed that in the opposite case, when the paraglider comes across a downdraft, his sink rate will increase because he is falling in a mass of descending air. He'll cover less distance than under stable air mass conditions. Here's another example where the wind influences the trajectory. The paraglider is flying in a crosswind. In this first case, the paraglider wants to fly over point A. However, he neglects to take into account the direction of the wind and ends up drifting off course. He'll have to correct his heading. With his new heading towards point A, he is now facing a headwind. As we've seen earlier, this situation drastically reduces his glide ratio. Depending on his altitude and the wind speed, he may not make it to his destination or even end up in the trees. In the second case, the paraglider takes into account the crosswind. This time he orients his canopy at a slight angle into the wind. This is called crabbing and allows him to stay on his heading and fly over point A. During flight, pay attention to conditions you come across. Adjust your trajectory early enough so that you stay on course and are sure to make it back to the landing field. Be particularly attentive during the approach and landing phases as they require a great deal of precision. An air mass is influenced by winds and thermal activity. Since a paraglider flies within this dynamic environment, it's understandable that these movements will influence it in turn. Let's start out by defining the 3 rotational axes of a paraglider: roll, pitch, and yaw. First off, let's look at a model showing the pilot and the paraglider's combined center of gravity. It's located just above the pilot's head. This right-to-left motion, called roll, is induced by the pilot or is caused when part of the wing comes into contact with a thermal. The second movement of the wing is the pitch. It's the wing's forwards-backwards movement. Like the roll, it is affected by air mass movements or controlled by the pilot, though in this case usually as an exercise. In order to adapt your piloting techniques during the flight, 2 important aspects concerning the pitch need to be understood and recognized. Later on, during your training and under an instructor's supervision, you'll learn how to make use of the following pitch exercise. But first, let's explain pitch movement. The pitch increases when the pilot or a thermal causes the wing to increase the angle of attack. This movement is followed by a recoil which we call the surge. Acting like a pendulum, the wing tries to recover its position over the pilot's head. It will therefore have to accelerate to catch up. The stronger the pitch back, the stronger the surge. The pilot must be ready to brake. Pilots need to understand how this pendulum-like effect is created by the pilot and the wing. At some stage during your training, you'll be expected to practice these pitch exercises in stable air with radio support. The final rotational axis of the wing is the yaw. It includes all movements along the vertical axis running from the pilot through the center of the wing. It can occur on the ground when inflating the wing, or in flight when the wind suddenly changes directions, in the presence of gusts, for example. As you progress through your training, you'll need to learn how to recognize and control these movements, which is called active flying. That way, you'll be able to adapt your piloting, keep the wing over your head, and be in total control of your paraglider. Let's now consider the last stage of any flight, the landing. The landing involves two phases, the approach pattern, or simply called the approach, and the final, which is the last leg of the approach before landing. An approach pattern allows you to better position yourself in relation to the landing target by gradually losing altitude. The approach pattern is part of the flight plan that your instructor sets up before launching. During your first flights, it is never improvised. Before taking flight, you should visit the landing field to get an idea of its layout and specific features. There are 3 indispensable rules for any approach. First, figure out the direction of the wind on the ground. Use the windsock to orient yourself so that the last leg of your pattern, the final, is facing the wind. Second, stay outside of the field near its edge and keep your eye on the landing target. Third, never turn your back on the field. This will prevent you from losing sight of the landing target. An S-turn landing approach allows the pilot to lose altitude by making a series of S-turns within a cone of safe airspace. The size of the S's decreases as the pilot loses altitude. By tracing smaller and smaller S's, the pilot loses enough altitude and lines himself up with the target for the final approach. When using this technique, turns need to be smooth and steady. Make sure you avoid steep turns near the ground. A series of figure 8 turns are used to lose altitude. The 8s get smaller and smaller so that the pilot can lose altitude and get in line with the landing field before his final turn. If the pilot overshoots the landing, he can trace different sized figure 8s to reposition himself. This type of approach is technically challenging. The pilot needs to know how fast his speed and altitude are changing in relation to the ground. This approach is ideal for a landing on a field surrounded by obstacles. The U, or standard aircraft approach, has 2 phases. This approach is also called constant aspect approach. The first phase. Without taking his eyes off the target, the pilot approaches the landing field along one of its sides. Though unusual, the pilot will be flying downwind during this phase. He needs to take this into account when assessing his airspeed. The second phase, the base leg. By looking at the target, the pilot will determine the best moment to make his first turn. The rest of the approach depends on this turn. The pilot needs to figure out how much distance he has left to cover, as well as the altitude he'll need before making the final turn. Whatever approach technique you choose to use, you should always end up with a long final. There are 2 keys to making a successful landing. The first is the wing stability. During the final, as the pilot gets close to the ground, he must keep the wing level and steady. And the second, the speed. A long final allows the pilot to increase his speed and build up energy that he can convert into a final flare. The flare will eliminate his vertical and horizontal speed and make a soft touchdown possible. Let's break down the phases of a landing. After entering the final approach, the pilot keeps his eyes fixed on the target with his arms up in order to increase the speed of his wing. Remember, however, to slightly apply tension on the brakes when turbulences are present. Only now can the pilot get into an upright position. He's ready to touch down at any moment. In order to land safely, the pilot must reduce his airspeed and ground speed to a minimum. This done by applying both brakes fully. This is called the flare. The flare is initiated 2 to 3 meters above the ground. This switch makes the wing pull out and produces a flare right before touchdown. An instructor will tell you when to make this switch by radio during your first flights. Be careful, each landing is different. The amplitude and the timing of this switch are determined by the wind speed. With experience, it'll become second nature. You'll discover the joy and comforts of making smooth touchdowns. The sky is an ideal playground for adventure, but it can quickly turn into a very uncomfortable place. This is why learning how to fly also requires a comprehensive understanding of meteorology. Before tackling the broad topics of macro and micro meteorology, you need to be aware of the following basic principle. Warm, humid air is lighter than cold, dry air. Keeping this physics rule in mind, let's take a look at some meteorological fundamentals that will help you better understand your future playground in the sky. The atmosphere is composed of perpetually moving air masses. To better understand these incessant movements, let's take a look at a model of our atmosphere from a planetary perspective. Our planet has two major air mass zones. The polar air zones, located at the poles of the Earth, which extend into some of Earth's temperate regions, and the tropical air zone forming a belt around the equator, which also extends into Earth's temperate regions. Why is there a difference between the temperatures of the polar zones and the zone near the equator? The sun's rays are parallel to one another when they reach the Earth, but not all of them arrive at a 90-degree angle because the Earth is a sphere. As a result, the polar regions are put at a disadvantage since at high latitudes, the same amount of radiant energy from the sun is spread out across a larger surface than at the equator. By scaling this surface to the length of a segment, the difference becomes clear. Segment A is longer than segment B. As a result, the ground located in the polar zones heats up less, as does the mass of air directly above it. And since cold air holds little water vapor, the polar air mass is relatively dry. On the other hand, the ground located in the tropical air mass zone is heated more efficiently. The heat energy from the ground then warms the air mass directly above it, and because a warm air mass holds more water vapor than a cold air mass, it will be more humid. The transfer of heat energy between the sun and the ground, or the ground and the air, deserve a few explanations. First off, radiation. Radiation is the process by which the infrared energy emitted from the sun is directly absorbed by an exposed solid, in this case the ground. This type of energy transfer primarily works with solids. It's far less efficient with fluids or gases. The second type of energy transfer is conduction. As far as solids are concerned, this is the easiest way to transfer heat. If one end of an iron bar is heated, the heat will rapidly spread to the other end. In our example, involving the ground and the air, the energy transfer takes place between two different substances, a solid and a gas. Having stored up thermal radiation from the sun, the ground then heats the air it is in direct contact with. And finally, convection. This type of molecular energy transfer occurs in fluids such as gases or liquids. Air masses transfer heat between one another through convection. A warm layer of air will expand and rise. Now that you know a little more about the types of heat transfer from one substance to another, let's look at the two air masses found at our latitude. On the one hand, you have a mass of cold, dry air called the polar air mass. On the other hand, a tropical air mass composed of warm, humid air that is less dense than the former. These two air masses, though radically different in regards to their temperatures and humidity levels, remain adjacent to one another without ever mixing. The boundary between the two air masses is called the polar front. As long as these air masses move parallel to one another, the polar front is said to be stationary. But in many cases, cold and warm air masses overtake one another, causing unstable wave-like undulations along the polar front. As the amplitude of an undulation between the two masses increases, a low-pressure system develops. Weather forecast bulletins on television shows us satellite images of these low-pressure systems. The white clouds are spiraling around a low-pressure center because of the thermal contrast between the cold and warm fronts. The center of this low-pressure system will grow and evolve. These systems are responsible for the weather conditions in our temperate regions. By observing the evolution of a weather system from the ground, we can make predictions about how the weather is going to change and consequently better plan for those changes. What can we observe from the ground? The arrival of a warm front. A warm air mass will rise above a cold air mass because it is less dense. The warm front has an almost vertical slope and moves slowly. The ground temperature increases slightly. The arrival of a warm front is first noticeable by the formation of clouds at very high altitudes, such as cirrus or cirrostratus. Then, as the warm front advances, rain clouds will begin to form at lower altitudes. Then, the cold front moves in quickly, behind the slower-moving warm front. The mass of cold air being denser, it undercuts the warm air, forcing it to rise. The warm air condenses quickly and abruptly, causing storm clouds such as cumulonimbus to form. The air mass becomes quite unstable. Ground level temperatures decrease. When a cold front catches up with a warm front, it's called an occluded front. After the cold front moves away, the sky clears up. Then, a high-pressure system, also known as an anticyclone, sets in. The front having passed, the sun's rays now are able to penetrate the clear skies and heat the ground, creating updrafts of air called thermals. Visibility is excellent. Cumulus clouds are present in the sky. This is the time for experienced cross-country pilots to fly. However, these conditions may not be suitable for inexperienced pilots and must be treated with a great deal of respect. By now, you should have an overall idea about the movement of air on a planetary scale. Let's now turn to micrometeorology, the motion and forces of air on a much smaller scale. Understanding certain micrometeorology principles is extremely important because they directly affect the quality and security of your flight. Your familiarity with the weather will increase with experience. Nevertheless, as with any discipline, you should be curious about it and you should already be observing your environment in order to better understand it. But also later to be capable of evaluating current and projected weather conditions so that you know when to fly and when to stay grounded. Now we know that the air we're flying through is in perpetual motion and that there is no such thing as perfectly calm air. Disturbed and chaotic air currents called turbulence can occur, as can more orderly updrafts of air called lift. Lift enables you to keep flying for long periods of time. There are two main types of lift. Dynamic lift is created as wind flows over hills and mountains. Thermal lift is caused by radiant heat emanating from the ground.
First, let's look at what causes dynamic lift. When an air mass cannot go around an obstacle such as a mountain but is forced to pass over it instead, the wind that climbs up over the obstacle creates a dynamic lift. Unfortunately for us, all obstacles and the airstreams they generate do not create exploitable dynamic lift. In order to create good dynamic lift, 3 conditions are required. First off, the airstream must be as perpendicular as possible to the obstacle. Secondly, the wind mustn't blow too strongly, otherwise it'll become turbulent as it travels uphill. Lastly, the shape of the obstacle. The shape of the obstacle is essential because the air will always find the shortest means of overcoming the obstacle. In the case of this conical hill-shaped obstacle, the wind follows the most direct route around its sides. In the case of a sufficiently wide and reasonably high landform, the wind stream climbs over it and lift is produced just before its summit. Let's look at how an airstream advances uphill and downhill. It's important that you understand this phenomenon, not only to make better use of the lift, but also to avoid the hazardous areas. A lift originates on the windward side of the mount near its summit. The higher you ascend in the lift zone, the weaker the lift becomes. To take advantage of the lift, you should make figure 8 parallel to the ridge, making sure to turn with your back towards the elevated ground. On the leeward side, things are completely different. The airstream does not create upward lift, but rather downward moving air currents that are very turbulent. The further you descend into this zone, the stronger the downdraft becomes. The presence of turbulence makes flying in these areas extremely ill-advised. Flying through dynamic lift will result in your first long-lasting flights. Taking advantage of this kind of lift is not difficult. It will give you the chance to get used to piloting your wing so that you will be better prepared for thermal lift. Thermal lift is another way to make your flights last longer. Warm, invisible air masses of different sizes will lift and carry paragliders up into the clouds. We're not going to give you a detailed technical explanation on how to take advantage of a thermal lift, nor how to fly in thermal lift conditions. However, we do want to provide you with some essential information that will be useful to you later on. How are thermals formed? Remember back to the different energy transfers we discussed earlier? Thanks to radiant energy from the sun, the ground is heated up. It should be noted, though, that this depends on the terrain. For example, a ground covered with snow will reflect more than 3/4 of the radiant heat as opposed to absorbing it. Afterwards, the ground will conduct its accumulated heat to the air directly above it. That heated layer of air will become warmer than the air around it, and as it warms, it becomes less dense and inevitably rises through convection. A difference of 2 degrees is all that's needed to make this pocket of warm air rise. If certain pressure and humidity conditions are reunited, a cumulus cloud will form at the top of the lift. As soon as the lift stops, the cloud is no longer supplied and it will eventually disappear. For paraglider pilots, the cumulus is the king of clouds. It is the sign of good flying conditions and above all, it indicates the presence of thermal lift. But there are also other clouds we need to be aware of. Distinguishing clouds is a difficult task because of the vast number of different observable cloud formations. This is why we're going to introduce you to the main clouds in each major family. Being able to recognize the clouds in the sky is very important before your takeoff, but also for anticipating the way the weather might evolve during your flight. Meteorologists have classified clouds according to 2 criteria: their altitude and their form. For the altitude, they have divided the troposphere into 3 layers.
the lower layer from 0 to 2,000 meters, the middle layer from 2,000 to 7,000 meters, and the upper layer from 7,000 to 11,000 meters. We can identify which layer a cloud belongs to by its prefix. Cirro for the upper layer, alto for the middle layer, and the absence of a prefix for the lower layer. The second criterion is the form. Two main cloud forms are distinguishable: layered clouds, which are referred to using the word stratus or strato, and accumulated clouds, the word cumulus and cumulo being used for them. Within the upper layer, we see cirrus, cirrostratus, and cirrocumulus clouds, which are mainly composed of small ice crystals. Notice the two letters you see before the name of each cloud. They represent the international abbreviation for each particular cloud. Within the middle layer, we find clouds composed of water droplets called altostratus or altocumulus. Finally, we see stratocumulus and stratus clouds at the lowest altitudes. Since we glide at that altitude, these are the clouds we usually pay attention to. Stratus clouds are the lowest. They form fog or white blankets of mist at the bottom of the valleys in the morning. Stratocumulus may at times cover the entire sky. They are generally grey. Then you have cumulus clouds which develop throughout the day due to thermal lift. This is why they are a paraglider pilot's favourite clouds. Finally, there are clouds with an impressive vertical development, such as cumulus congestus, nimbostratus or cumulonimbus. These clouds belong to several levels at the same time. Cumulocongestus are cumulus clouds that have kept on developing vertically. Their bulging shape is typical. At this point, they become very dangerous clouds for our activity. A nimbostratus cloud is very dark at its base and quite thick. It's a rain cloud. Because of its strong vertical development, and more so because of its lack of visibility, it is a dangerous cloud for free flight. Then there are cumulonimbus clouds which can develop and extend as high as 12,000 meters. This cloud is by far the most powerful. You're better off admiring this type of cloud from the ground. For mountain flying, when flying early in the morning, you need to wait patiently for the sun to warm the hills because this is what creates the first breezes of the day. Let's look at how breezes originate and how they evolve throughout the day. Breezes are a localized phenomena that depend on a specific location's topography, vegetation, and most importantly, its exposure to the sun. Throughout the day, the sun will warm the hillside, causing the ground temperature to increase more rapidly than the water temperature. These conditions are what causes a breeze. The ground will warm the air above it through conduction, making it less dense or lighter and causing to rise. The result is a lift. And since nature hates vacuums, the space left free by the ascending air must be filled. The land in this case becomes a vacuum, sucking in air from the sea. A sea breeze fills in the void created by the convection. At night, the exact opposite takes place. The land cools much faster than the sea, creating the necessary conditions for a new breeze. This time, the air over the sea is warmer, hence it rises, generating a vacuum that sucks the air from land out to sea. This is called the land breeze. It usually isn't as strong as the sea breeze. Let's observe how the same phenomena occurs during various landforms, starting out with the morning. The radiant heat from the sun warms the eastern-facing hillsides. The hillsides then conduct that heat to the air above it. This air, having been rendered less dense, rises up the length of the hillside. These are called uphill breezes. Learning how to paraglide under these conditions is ideal. The gentle, uphill breezes will help inflate your wing, and you will experience little turbulence in these slightly elevating air masses. Throughout the morning, this phenomenon increases in intensity until around midday. This is when the sun is almost vertically overhead, which causes the greatest uphill breezes on the southern-facing hillsides. These breezes, called valley breezes, move in to fill the void left by the rising warm air. Late in the afternoon, the eastern-facing hillsides begin to cool off and the air becomes heavier. This air falls down the hillside, creating downhill breezes. These breezes help fill the void in the valley, as well as the one created along the sun-exposed westward hillsides. At sunset, air temperatures at higher altitudes are cooler than those in the valley or along the plain. Downhill breezes move in to rebalance the system. Certain phenomena, such as turbulence, can make a flight uncomfortable and dangerous. You should be comforted by the fact that during your training, you'll be flying under calm conditions and on familiar sights, all the time accompanied by experienced instructors. Nevertheless, recognizing and understanding these hazards is the first step towards knowing how to avoid them. Let's begin by looking at turbulence. Turbulence comes from the chaotic movement of air within an air mass. They can be divided in two main types: obstacle turbulence and shear turbulence. Let's first look at obstacle turbulence. When the wind blows over an obstacle unevenly and discontinuously, turbulence forms. Air constantly flows up to the top of the windward side of this landform, but as soon as the air passes over to the leeward side, a depression forms, generating turbulences called rollers and rotors. There may also be areas of the windward side where turbulence occurs. For instance, if the windward side is hilly or irregular, turbulence will form in the immediate vicinity of the obstacle. Of course, in some cases, the obstacle generates no turbulence at all, neither on the windward side nor leeward side, such is the case here, where this particular landform creates a dynamic lift. Similarly, the airflow on the leeward side of obstacles such as a hedge of trees or a house can also be turbulent. For this reason, landing downwind of such obstacles is not recommended. Let's now turn to the other type of turbulence, shear turbulence. Shear turbulence occurs where two air masses move against one another. This is the case around a thermal lift, since warm air rises in the center and cooler air descends around it. When you fly into a thermal, you will feel the effect of this shear turbulence on your wing. Another example of shear turbulence you're likely to encounter when flying is the case of two superimposed air layers that are moving in opposite directions. Shear turbulence is present along the border separating the two layers. When a fluid such as wind passes through a narrow or restricted passage along its trajectory, its speed increases. This is known as the Venturi effect. Let's use the example of wind blowing over a hill. At point A, the lower and upper winds are traveling at the same speed. At point B, the lower we descend into the air mass, the faster the wind speed is. Notice that the winds closest to the hill are the fastest. In fact, the wind is being compressed between the hill and the weight of the atmosphere. At point C, near the top of the hill, the speed is the highest because the atmospheric weight forces the wind through a narrow passageway. So as to ensure a constant flux, the wind is forced to catch up by accelerating. We also see the Venturi effect occur when wind travels through a mountain pass. As the wind blows through the pass, the airstream will be compressed. Like the wind blowing alongside the hill, it will also speed up as it makes its way through the narrow passageway. The wind gradient is the variation of wind speeds at different altitudes. This phenomenon is present at any altitude in our atmosphere, but the wind gradient we are interested in is the one where wind speeds decrease at low altitudes close to the ground during our landings. That is, at altitudes less than 50 meters from the ground. Why does the wind speed slow down? The air is a fluid with a certain viscosity that sticks to obstacles. In doing so, it loses a lot of its energy. The further we descend, the slower the wind will blow because of the gradient effect. This effect is present on fields full of obstacles such as hedges, but be careful. It may also be present on flat, obstacle-free fields. During landing procedures, the pilot must be extremely vigilant when dealing with the wind gradient. As soon as the wing encounters the gradient, it will lose relative airspeed. The only way to make up for the lost speed is to lose altitude. The wing will accelerate by itself, and in some cases it will roll off. Maintaining a sufficient amount of speed during the final approach is recommended to deal with this effect, an effect that can be dangerous close to the ground. Make a note of the fact that the altitude loss is directly proportional to the gradient's intensity. Learning the rules and regulations is an important part of your training. Thoroughly understanding them will make the activity safer, allow you to anticipate and avoid potential hazards, and gain precious time in case you have to make a quick decision. They'll determine your course of action depending on the location of your flight, the presence of other aircraft in the same airspace, or weather conditions and other criteria that we're going to look at. The rules we'll cover in this chapter are internationally accepted and enforced in most countries. We've done our best to point out exceptions. As a rule, however, you should always keep in mind that rules may differ from one country to another. Before leaving to fly abroad, find out about the regulations of the country you're visiting and remember to respect local laws. You'll usually find them on the website of the National Federation. The increase in air traffic over the years has led civil aviation authorities to create aircraft categories and rules to establish priority. As we've just seen, each category of aircraft has a different degree of priority. Sailplanes, hang gliders and paragliders all belong to the same category. In reality, questions of right-of-way will mostly arise with other paragliders or with hang gliders. Flying in the same airspace as sailplanes or private airplanes is rare. Let's go over the rules of priority that prevent paragliders from colliding. The prime rule is the following. It's the pilot's responsibility to take all possible measures to avoid a collision with any other aircraft. The animations that follow present the collision avoidance rules. They are not to scale. Try to maintain a safe distance from the other aircraft. First situation. Two paragliders are approaching head-on with a risk of collision. In this case, both aircraft shall alter course to the right. In case of hill or ridge soaring, this rule is modified. Two paragliders are approaching head-on when ridge soaring. The pilot with the ridge on the left should move out so that the other can maintain course without having to turn into or over the ridge. New situation. Two paragliders have converging courses. When two aircraft of the same classification converge at approximately the same altitude, the one with the other on its right shall give way. On the right is in the right. In flight, if you come across a situation like this, act as quickly as possible. It's pointless to wait till the last minute before reacting, moving out of the way and scaring both yourself and the other pilot. Because each wing has its own technical specifications, your paraglider may fly faster than others. Passing someone is permitted. Internationally, passing is typically done on the right. The aircraft being passed has the right of way, except in Italy where the glider overtaking has priority but must allow enough safety clearance. The glider being overtaken gives way, avoiding any change in direction that might interfere with the overtaking glider's path. Also, in England and in Italy, in free space away from a hill, paragliders can pass on the left as well as the right. When ridge soaring, a paraglider overtaking another glider that is flying in the same direction should pass between the ridge and the glider being overtaken. If you're overtaking the pilot and there is no room to pass, just turn back. When thermaling, the first pilot to enter a thermal establishes the required turning direction in that thermal. All paragliders joining shall circle in the same direction as any other gliders already established in the lift. In order to keep the sky safe and accident-free, you must know these rules. Nevertheless, be flexible when flying. Don't rely on others to always respect your right of way. Faced with a disrespectful or inattentive pilot, you're better off abandoning your priority and changing your heading. Anticipate these situations early and react decisively so that other pilots flying around you know what your intentions are.
My name is Russell Ogden. I work for Ozone Paragliders as a test pilot. I work with David Dagoult and Jérôme Canot in the test team. The company is an Anglo-French company that was created by a group of Englishmen. We're based in France and it's about 50-50 with English and French people. Mostly we fly in the Côte d'Azur area. We fly at Gourdon, at Col de Blaine, La Chaise, Roquebrune, all in the south coast of France. Designing a paraglider is a complex process and has many stages throughout its development. First off, we have to agree and decide the type of wing that we're going to build, whether it's a beginner wing or a cross-country wing or competition wing or so on. And so we agree all the parameters that we're trying to aim for, and David de Gaulle is in charge of the design process, and he designs that glider using CAD software on a computer and 3D modelling and so on, which is then sent to our factory in Vietnam. We have our own factory in Vietnam which makes all of our gliders and prototypes. We have a special team in Vietnam whose sole job is to make and cut the prototype wings, which takes about 4 or 5 days from the moment David sends it till we receive it. Once we have the prototype, then it's the job of the test team to test the glider. What we're looking for initially is the feel, making sure that the glider feels good, all the lines are the correct length, the tension of the sail is good, it's not too loose or floppy or not too tight. And we really work on the handling and how the glider reacts in the air through just normal flying, how it feels in a thermal, how it feels in ridge soaring, if it has a good sink rate or a bad sink rate. And we really try and put our feelings and explain our feelings together so that we can agree on where we need to go with our development. What we're fiddling with and changing is often the tension in the sail, how much tension we have at the leading edge or trailing edge, as well as all the line lengths and so on. How much arc there is in the glider as well is very important. Once we're happy with conceptually we're happy with what we have, we then really go through the DHV testing stage where we're trying to find out how it reacts when it all goes wrong, when we have deflations and so on. So we're testing for asymmetric deflations, symmetric deflations, the stall, the spin, beeline stalls, big ears, and importantly, especially with the beginner gliders, is how they inflate, how they launch, how they feel on the ground. They're not shooting too much, or they're not sitting back on the takeoff as well. The whole process differs from glider to glider, but generally you're looking between 6 months to a year to get a final product that we're happy with and would release and would sell it.
Time to kick some ass.
There's loads of places that you can get information these days. The internet is probably the best place. If you do a search on the internet for paragliding, you'll get lists of pages and lots of schools in your local area or the whole country. You can also contact the National Federation in each country, and they will be able to give you a list of all the schools that are available. Choosing a school depends on your area. The best thing to do is if you know someone who flies, is to ask their opinion. But otherwise, just go for your local school, because sometimes the learning process can take some time, so you don't want to be in a school that's maybe 300 kilometers away. So going to a local school, I think, is important, so that you can give the sport time and give it your weekends, which is basically what you need to be able to fly properly. Once you learn flying, I'd say the important thing is continuity. Rather than doing some days and then having a few months off and going back to it, you never get past that first stage. If you can do several days in a row, or preferably a week course, then you'll get a much better understanding and you'll progress much faster, because you're not always taking those backward steps that long breaks entail. So doing a week course is a very good idea, or if you can't take the time off work, then devoting your weekends to learning to paraglide is really important. And that carries on throughout your whole flying career. It's really important that you remain continuous in your learning process and you don't get too rusty. I think the most important thing whilst you're learning and throughout your whole flying career is ground handling, is being able to control your glider on the ground. The takeoff is probably the area where there's most accidents, and it's the most dangerous part of the flight. So being perfect at your takeoffs is the aim, and that should never stop throughout your whole flying career. It's something that you always practice, especially if you have a period where you haven't flown for a while. Then just putting half an hour in on the ground is really useful for you. Not only does that keep you safe on the takeoff, but when you're flying in the air and you start flying in more demanding conditions, when there's stronger thermals and so on, then the skills at keeping the glider inflated on the ground are directly transposed? What's the word? Are directly related to the way that you control your glider in the air. So if you have very good skills on the ground and you can keep your glider inflated in a gusty wind or a light wind, then you'll be able to do so in the air more easily. You'll also be more relaxed, which is really important for flying. If you start to get scared and you start to tense up, then your actions and your movements are not so good. If you can be relaxed, then you'll be able to think a little bit more clearly and keep the glider flying safer. When learning to fly or when flying, fear is a major part of our sport. We're not designed to fly at all, we're terrestrial beings. So overcoming those fears is a very important part of flying, but also having those fears are very important, because without fear you can start maybe doing reckless things, flying in conditions that you shouldn't be flying or on wings that you shouldn't be flying. Fear happens to all pilots. Every pilot goes through it, no matter what level they're at. And being able to control those fears are really important. Often fear, or that inner voice that you have, is telling you something important, and you should always listen to your inner voice. Often fear comes down to the fact that maybe you feel that your skills are not up to it, which means that, well, maybe you should take a step backwards and practice your ground handling more, or practice simple flying in smooth conditions more before you start progressing on to flying in thermic conditions or off big mountains or so on. So I think fear is a very important part of flying, and it's what keeps us alive. And the moment that you lose fear is the time that you should be careful, because that's when you might start to try and overextend yourself, maybe stepping up a glider level that's too much for you, or flying in conditions that are too strong. Flying a glider is exciting, but there's so much choice out there that it's very hard as a new pilot to make an informed decision. The thing I would recommend is to listen to your instructor and take your instructor's advice. Some people will try and sell you gliders that are cheap and maybe old, and I don't recommend doing that. When gliders get old, they become less safe, their flying characteristics change. So if you can afford it, I'd always buy a new glider, and I'd go for a level of glider that your instructor feels is right for you. Nowadays, the best bet is, as a first wing, is to fly a DHV1 glider. They're designed specifically for new pilots. They're easier to take off, they're easier to ground handle, they're less likely to deflate, and if they do deflate, then they're far better behaved than some of the other wings, the more high performance wings. So the DHV1 gliders are more forgiving, and yet they're still great fun to fly. They're still brilliant in thermals, they can climb really well. They lose a little bit of performance on glide, but it's only a very small amount, and it's only really noticeable if you're using your speed bar a lot, which generally as your first wing you don't use so much. So yeah, I'd go for a DHV1 glider, and I'd go for as new a one as I can get, and put your time and learn the sport in the safest possible way. Paragliding is a dangerous sport. You need to reduce the danger, and you do that by getting the best equipment you can. The harnesses these days, you can get large Cygnus type airbags which inflate underneath you. They're a great idea for a new pilot. So when you're learning, the best thing to do is to trust your instructor. is to listen to your instructor. Invariably, they'll be very experienced, they may have been flying for a long time, and they've taught many people, so they know how people learn, and they can change the way they teach to different standards of students. So trust your instructor, listen to your instructor, and follow the advice of your instructor. Afterwards, it comes down to practice, and it comes down to dedication, and you need to put the time in on the ground, forward launching, reverse launching, all the different methods of launching. Around Europe, you'll see different types of pilots. In England, for example, people generally are relatively good at reverse launching because we fly in wind a lot, but they hate to do forward launches. In France, sometimes it's the other way around. You don't see pilots doing many reverse launches, but they always want to forward launch. So if you do have a weakness, if you feel that, I don't use forward launch because I'm not very good at it, then that's telling you that's something you need to work on. The aim is to try and perfect and try and become as rounded a pilot as you can. So throughout your flying career, you want to look at areas that you're not comfortable with and maybe consider learning about those areas. Also, going on advanced courses is important. Once you're qualified, that's not it. There's still the whole game to learn. The aim of a school is to make you into a person who is safe and knows the dangers of the sport. Once you leave that school environment, that's when it can become dangerous. So taking advice from other pilots on the hill is really important. If there's more experienced pilots that are not flying, there's generally a reason for it. So it's always good to ask people to introduce yourself as a new pilot and get as much information as you can. Absorb as much information as you can. Watch every DVD there is, read every book, try and get all the information you can. There's also advanced courses where you can learn how to thermal correctly under guidance, how to fly cross country, and flying cross country from country to country is different. If you generally live in an area of flatlands, then when you come to the mountains, it's a different game altogether. So it's a good idea to take advice, to take professional advice, so that you don't put yourself into a dangerous position without even knowing it. As your skills develop and you fly potentially in more strong conditions and on more high performance wings, that might be the time that you want to consider doing an SIV course, where you learn how to control your glider in abnormal conditions, i.e. if it's had a deflation and so on. It's best to do that in a safe, controlled environment, over water with a life jacket and an instructor, rather than to discover what a deflation is like when you're 10 metres above a cliff face. So SIV courses are not the be-all and end-all of becoming a good pilot, but they certainly help you become a safer pilot and make you feel and understand the wing a lot better.